Welcome back to EGME-333. In today's video, we're going to discuss the topic of manometry. In the field of fluid mechanics, manometers are devices that use vertical or inclined liquid columns to measure the pressure difference between 2 points or between a certain point and the atmosphere. Examples include a piezometer, as shown in this diagram, a U-tube manometer, as shown here, and an inclined manometer, as shown here. In all three examples, the manometers involve columns of liquids at rest, so the pressure given at a specific point, P, is given to us by a reference pressure, P sub ref, plus the specific weight gamma times the depth h relative to the reference pressure. For example, if we wanted to utilize a piezometer, which is defined as a vertical tube with an open top that is attached to a point where the pressure is desired, in this case point A, we can work with the previous equation to determine the pressure at point A by indicating first the specific weight of the fluid gamma and noting that the pressure at point A is the same value as the pressure of the flashing point. The reason for these 2 points sharing the same pressure is that the depth between them is 0, since they are at the same vertical position. So if we know the depth of point A relative to the open end of the piezometer indicated by H, then we can determine the absolute pressure at point A as P sub A simply by saying that P sub A is equal to the reference pressure. In this case, that is the atmospheric pressure at the open end or top of the tube, plus the specific weight of the fluid gamma times the depth of the fluid. Note that if we wanted to determine the gauge pressure of point A, delta P sub A, then we can define or compute the gauge pressure by taking the absolute value of pressure at point A, P sub A, and subtracting the atmospheric pressure, P sub ATM. By combining the two previous equations, we can determine that the gauge pressure at point A, delta P sub A, is simply equal to the product of the specific weight gamma times the depth h. Note that for a piezometer, as the liquid height h increases, then the corresponding gauge pressure delta P sub A also increases. Next, let's look at a U-tube manometer, which consists of a tube that is formed into the shape of a U, as shown in the diagram below. One end is connected to point A, whereas the other end of the U-tube is open to the atmosphere, similar to the piezometer. However, what you'll notice is that in this example, we are dealing with two separate fluids. We have the fluid corresponding to point A, which is labeled as gamma sub 1, and we have a second fluid that is in the U-tube manometer, gamma sub 2, which we refer to as the gauge fluid. When working with U-tube manometers, we want to adopt the following approach for determining the pressure at point A. Typically, we'll stick with the following 3 rules. First, we'll note that the pressure increases as one goes down a liquid column. So the pressure at the bottom of a column, P sub down, should always equal the pressure at the top of the column, P sub up, plus the specific weight of the liquid within the column times the absolute value of the vertical displacement, delta Z. For example, if I knew the value at the pressure at point 1 and I was interested in the value of the pressure at point 2, I can, number one, argue that the pressure at point 2 should be higher than the pressure at point 1 because point 2 is at a lower elevation than point 1, and that the value at point 2 is equal to the pressure value at point 1 plus the product of the specific weight of the fluid between them, gamma sub 1, times the absolute value of the vertical distance between the 2 points. Number 2, the pressure decreases as one goes up a liquid column. So the pressure at the top of a liquid column, P sub up, is equal to the pressure at the bottom of a liquid column minus the specific weight of the liquid times the absolute value of the vertical displacement. For example, if I knew the value of the pressure at point 3 and I was interested in the value of the pressure at point 4, I could argue that the value for the pressure at point 4 should be lower than the value of the pressure at point 3 because point 4 is at a higher elevation point than point 3. And that the value of the pressure at point 4 should equal to the value of the pressure at point 3 minus the specific weight of the fluid gamma sub 2 times the absolute value of the vertical displacement between them. Lastly, any 2 points at the same elevation in a continuous region of the same liquid are at the same pressure. In this case, look at the pressures at P2 at point 2 and point 3. For example, if I know the pressure at point 2 and I'm interested in the pressure at point 3, I could argue that these 2 points share the same value in pressure because, number one, they are at the same elevation or vertical position, and between point 2 and point 3, it's the same liquid that connects the 2 points. So let's take these ideas and apply them as we go from point A all the way to the opened end of this U-tube manometer. So let's start off at point A, where we should have a corresponding pressure P sub A. And if we go from point A to point 1, we'll note that point A and point 1 are at the same vertical position. So they should have the same pressure. Next, we'll go from point 1 down to point 2, where they have a vertical displacement of h sub 1 between them, as shown in the diagram. So given that we're going down in vertical position, we can say that the pressure should increase. Therefore, to P sub A, I'm going to add the product of gamma sub 1 times h sub 1. From point 2, I'm going to move over to point 3. Again, between point 2 and point 3, they are at the same vertical position and they have the same fluid connecting the 2 points. So they must share the same pressure. So no changes in pressure to the overall quantity yet. Lastly, I'm going to go from point 3 up to point 4 and travel a vertical distance of h sub 2. Because I'm going from point 3 to point 4 and I'm increasing my vertical position, I should expect a decrease in pressure. Therefore, I'm going to subtract the product of gamma sub 2 times h sub 2 from the total quantity. And we know that at point 4, that is the opened end of the tube. So at point 4, all of this should equal the atmospheric pressure. So going from point A all the way to point 4, I should essentially get to the atmospheric pressure P sub ATM. Now, the point of interest is point A, so I can simply solve for point A and get that the absolute pressure at point A, P sub A, is equal to the atmospheric pressure P sub ATM plus the product of the specific weight gamma sub 2 times h sub 2 minus gamma sub 1 times h sub 1. If I was interested in the gauge pressure at point A, I can subtract the atmospheric pressure and end up with the gauge pressure at point A as gamma sub 2 times h sub 2 minus gamma sub 1 times h sub 1. One big advantage of a U-tube manometer is that the gauge fluid can be different from the fluid where the pressure is measured, as shown in this case.